August 3rd, 1942. Guadalcanal, Solomon Islands. Lieutenant Commander Masao Sato stood on the beach near Lunga Point, examining fragments of an American 5-inch anti-aircraft shell that had detonated above his position 3 days earlier. The shell had not struck anything. It had simply exploded in mid-air, approximately 50 meters above the Japanese transport vessel Kinryu Maru, as it attempted to unload supplies. Sato turned the nose cone over in his hands. The fuse mechanism was unlike anything in the Imperial Japanese Navy's arsenal. No impact was required. No timing mechanism that he could identify. The shell had detonated at precisely the moment it came near the aircraft, as if it could sense the target's presence. This should not be possible. Fuses required contact or preset timing. Those were the only two methods of detonation known to military science. Yet here was physical evidence of a third method, one that seemed to violate everything Sato had learned at the Imperial Japanese Naval Academy and in 7 years of service as an ordnance specialist. The fragments would be shipped to Japan for analysis. What Japanese scientists would discover would fundamentally alter their understanding of American technological capability and their assessment of whether the war could be won. The journey to this moment had begun not with Japanese discovery, but with American desperation. In the late 1930s, as war spread across Europe and Asia, American naval planners confronted an unsolvable problem. Aircraft threatened ships in ways that existing defenses could not counter. Dive bombers could deliver bombs with devastating accuracy. Torpedo bombers could strike from low altitude, below the reach of heavy anti-aircraft guns. Level bombers could attack from high altitude, beyond the effective range of light weapons. The problem was not firepower. American ships carried extensive anti-aircraft armaments, 5-inch 38 caliber. Dual-purpose guns could engage aircraft at ranges exceeding 10,000 yards. 40mm Bofors guns provided medium-range defense. 20mm Oerlikon cannon offered close-range protection. The problem was hitting the target. Anti-aircraft fire in the 1930s and early 1940s relied on shells with mechanical time fuses. Gunners calculated the distance to the target's speed and direction, the shell's flight time, and the wind conditions. They set the fuse to detonate at the calculated moment. The shell was fired. It traveled toward where the target was expected to be. If every calculation was correct, if the target maintained course and speed, if wind conditions remained constant, if the fuse timing was precise, the shell would detonate near the aircraft. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The reality was that aircraft rarely maintained predictable courses. Pilots could see anti-aircraft fire. They could observe shell bursts and maneuver to avoid predicted positions. A bomber approaching a ship would not fly straight and level while anti-aircraft shells exploded around it. The pilot would jink, climb, dive, turn, making constant unpredictable changes that defeated calculated fire control solutions. Combat statistics from the early years of World War II revealed the brutal mathematics of anti-aircraft effectiveness. British forces fighting in the Mediterranean calculated that it required approximately 2,500 rounds of anti-aircraft ammunition to down a single enemy aircraft. American forces in early Pacific engagements reported similar figures. The USS Enterprise during the Battle of Midway expended thousands of rounds of anti-aircraft ammunition while engaging Japanese aircraft. The hit rate was measured in fractions of a percent. The problem was not the guns. American 5-inch 38 caliber weapons were among the most advanced anti-aircraft guns in the world. The Mark 37 fire control director could calculate firing solutions with remarkable precision. Trained gun crews could maintain impressive rates of fire. But none of this mattered if shells exploded in empty air, while aircraft flew unharmed through the gaps between bursts. Mechanical time fuses required that shells detonate at a specific moment. Aircraft that were not at that specific location at that specific moment were safe. The Japanese had recognized the identical problem. Their solution, developed in the mid-1930s, was to accept the limitations and focus on volume of fire. Japanese doctrine called for massed anti-aircraft guns, creating barrage zones of exploding shells. Aircraft entering these zones would face such dense fire that maneuverability became irrelevant. Some shells would detonate close enough to damage targets through shrapnel effect. Required enormous quantities of ammunition. It required multiple gun batteries firing simultaneously. It worked only when defending fixed positions where gun emplacements could be concentrated. It provided no solution for protecting individual ships or mobile forces operating beyond the range of massed shore-based guns. American planners in 1939 recognized that a fundamentally different approach was needed. Mechanical time fuses would never provide adequate protection. The shell itself needed to detect when it was near a target and detonate at the optimal moment for maximum lethality. This required a proximity fuse, a device that could sense a nearby aircraft and trigger detonation without physical contact. The concept was not new. Patents for proximity fuse designs existed from the early 1900s. British inventors had proposed radio-based proximity detection in the 1920s. The technical challenges had proven insurmountable. A proximity fuse would need to contain a complete radio transmitter and receiver, small enough to fit inside a 5-inch shell. It would need to function reliably after experiencing acceleration forces, exceeding 20,000 times the force of gravity during firing. It would need to resist the centrifugal forces from the shell's rotation at more than 20,000 revolutions per minute. It would need to operate on battery power for the few seconds of shell flight. It would need to distinguish between actual targets and ground clutter, clouds, or sea surface returns. It would need to be manufacturable in quantities of millions at costs that permitted expenditure in combat. Every requirement seemed to contradict the others. Electronics that could survive 20,000 G acceleration did not exist. Vacuum tubes that could function while spinning at 20,000 revolutions per minute had never been built. Radio circuits small enough to fit in a shell casing while leaving room for the explosive charge, and mechanical components were beyond current technology. Battery systems that could provide reliable power under combat conditions while withstanding firing shock were theoretical concepts without practical implementations. In May 1940, as German forces swept through France and the collapse of Western Europe seemed imminent, the United States Navy authorized development of what would be called the VT fuse. The designation stood for variable time, a deliberate deception to conceal the true nature of the weapon from potential enemies. Development would be led by Section T of the National Defense Research Committee, soon reorganized as Division 14 of the Office of Scientific Research and Development. Merle Tuve, director of the Department of Terrestrial Magnetism at the Carnegie Institution in Washington, took charge of the program. Tuve was not a weapons designer. He was a physicist who had spent his career studying the ionosphere, developing techniques for probing the upper atmosphere using radio waves. His expertise in radio propagation and receiver design made him uniquely qualified to lead the proximity fuse development effort. Tuve assembled a team that would eventually include over 800 scientists and engineers working at facilities across the United States. The Johns Hopkins Applied Physics Laboratory in Maryland became the primary development center. The National Bureau of Standards contributed testing facilities. The Carnegie Institution provided research support. Private contractors, including Westinghouse, General Electric, Sylvania, and Raytheon, would eventually produce components and complete fuse assemblies. The team confronted each technical challenge systematically. The acceleration problem required vacuum tubes that could survive forces that would instantly destroy conventional electronics. Standard vacuum tubes used thin glass envelopes containing wire filaments. Under 20,000 G acceleration, the filaments would shatter and the glass would fracture. The solution came from developing tubes with much heavier construction, thicker glass envelopes, shorter, heavier filaments, internal structures braced to resist acceleration forces. The tubes were tested by firing them from naval guns and examining the survivors to understand failure modes. Hundreds of tube designs were built, tested, destroyed, and redesigned. By early 1941, tubes existed that could survive firing shock with reasonable reliability. The rotation problem proved equally challenging. At 20,000 revolutions per minute, centrifugal forces would throw the tube's internal elements outward, potentially shorting circuits or breaking connections. The solution required symmetric tube construction, where every element was balanced around the central axis. Filaments were wound symmetrically. Anodes were constructed as cylinders rather than plates. Every component was designed to function under extreme centrifugal loading. The size constraint forced radical miniaturization. Standard radio receivers in 1940 contained dozens of vacuum tubes, each the size of a small light bulb. The VT fuse would need to compress an entire functioning radio transmitter and receiver into a space measuring roughly 4 inches in length and 2 inches in diameter, while leaving room for the battery, the firing mechanism, the safety switches, and the detonator. Engineers developed tubes barely 1 inch in length. They designed circuits that performed multiple functions with single components. They eliminated every unnecessary element, stripping the radio design to its absolute minimum while maintaining functionality. The prototype fuses by mid-1941 contained 5 vacuum tubes, performing the functions that would have required 15 tubes in a conventional radio set. Power supply presented its own set of problems. The fuse needed electrical power from the moment it left the gun barrel until detonation, typically 15 to 20 seconds. The battery had to survive firing shock, provide stable voltage under extreme conditions, fit within the tight space constraints, and function reliably across temperature ranges from below freezing to above 100 degrees Fahrenheit. Standard batteries could not meet these requirements. The team developed a specialized battery using chemicals and construction techniques designed specifically for the VT fuse application. The battery was tested by firing it from guns, spinning it in centrifuges, heating and cooling it through extreme temperature cycles, and measuring its output under conditions that simulated combat use. By late 1941, reliable batteries existed that could power the fuse through its flight profile. The radio circuit itself used the Doppler principle to detect targets. The fuse transmitted a continuous radio signal at approximately 180 MHz. When this signal reflected off a moving aircraft and returned to the fuse's receiver, the reflected signal was shifted in frequency due to the relative motion between the shell and the target. This frequency shift, called Doppler shift, could be detected electronically. When the Doppler shift indicated that the shell was approaching a target at high speed, the fuse triggered detonation. The system required extraordinary sensitivity. The reflected signal from an aircraft was weak, easily masked by noise or interference. The circuit had to distinguish between legitimate targets and false returns from clouds, sea surface, or ground clutter. It had to function while the shell was rotating, spinning the antenna through space at tremendous speed. It had to provide reliable detonation signals while rejecting spurious triggers that might cause premature explosions. Engineers spent months refining the circuit design. They tested prototypes against aircraft flying at various speeds and distances. They measured performance in different weather conditions. They fired shells over water and over land to understand how different environments affected the radio returns. They developed filtering circuits that could distinguish aircraft from background clutter with acceptable reliability. By early 1942, the VT fuse existed as a functioning prototype. The device could survive being fired from a 5-inch gun. It could detect aircraft. It could trigger detonation at the optimal moment for maximum lethality. But moving from prototype to production required solving an entirely different set of challenges. The fuse was complex. It contained over 200 individual components. Every component had to be manufactured to precise tolerances. Every component had to be assembled in the correct sequence. Every fuse had to be tested to ensure it would function when fired, and production would need to reach millions of fuses per year to meet military requirements. American industry mobilized for VT fuse production with the same intensity it brought to aircraft and ship construction. Factories that had produced radio tubes for civilian receivers were converted to produce the specialized tubes for VT fuses. Machine shops that had made automobile components now manufactured fuse bodies and mechanical parts. Assembly lines were established at multiple facilities to spread production and reduce vulnerability to any single point of failure. Quality control was absolute. Every fuse was tested electronically before shipment. Random samples were fired to verify performance. Failures were analyzed to identify manufacturing defects or design weaknesses. The production process was continuously refined to improve reliability and reduce costs. By summer of 1942, production reached several thousand fuses per month. By early 1943, production exceeded 100,000 fuses per month. By late 1944, American factories were producing over 400,000 VT fuses monthly. The total wartime production would exceed 22 million fuses, representing one of the most remarkable feats of technical manufacturing in military history. The first combat use of the VT fuse came in January 1943 during the Battle of Rennell Island. The cruiser USS Helena fired VT-fused 5-inch shells against Japanese torpedo bombers attacking American ships south of Guadalcanal. The results were immediate and dramatic. Shells that would have normally exploded in empty air now detonated at the precise moment they passed near enemy aircraft. Bombers that had previously maneuvered between shell bursts now found that the shells followed them, detonating whenever they came close. One bomber was hit directly when a shell exploded within 20 feet of the aircraft, tearing off the tail section and sending the plane spinning into the ocean. Another suffered severe damage when a shell burst alongside, shredding the wing with shrapnel. A third attempted to evade by diving toward the water and was destroyed when a VT-fused shell exploded directly above it, driving the aircraft into the sea. American gunners, watching the engagement, could not fully understand what they were witnessing. The shells appeared to be hunting the aircraft, detonating at the perfect moment without any apparent reason. The gun directors had not changed. The fire control was identical to previous engagements, but suddenly, every shell burst was near a target. The hit rate increased by an order of magnitude. Aircraft that would have escaped unharmed through conventional anti-aircraft fire were being damaged or destroyed. For Japanese pilots flying those missions, the experience was terrifying and inexplicable. They had learned through bitter experience how to evade American anti-aircraft fire. Watch for the muzzle flashes. Count the seconds of shell flight time. When the first shells of a barrage exploded, change course immediately. The next salvo would be aimed at where you were, not where you are now. The tactics had worked for months. Pilots who mastered evasive maneuvers could penetrate American anti-aircraft fire with acceptable losses. But on this night in January 1943, the old tactics failed completely. Pilots maneuvered as they had been trained. They watched for shell bursts and changed course, but the shells still exploded beside them, around them, above them. The fire pattern made no sense. Shells were detonating when they should have exploded in empty air. Barrage patterns seemed to follow aircraft through evasive maneuvers. Multiple pilots reported what seemed like impossibly accurate American gunnery, shells exploding at precisely the right moment, regardless of aircraft maneuvers. The Japanese pilots who survived the Rennell Island engagement reported the phenomenon to their commanders. Their reports described shells that appeared to track aircraft, detonations that occurred at optimal range regardless of evasive action, the anti-aircraft effectiveness that exceeded anything previously encountered. Intelligence officers were skeptical. The reports seemed exaggerated, the product of stress and combat fatigue. Anti-aircraft shells could not track targets. They were not guided weapons. They exploded at a preset time or upon impact. The fundamental physics of artillery fire did not permit the kind of behavior the pilots described, but as more reports accumulated from subsequent engagements, as more pilots described similar experiences, as loss rates from American anti-aircraft fire increased dramatically, Japanese naval intelligence recognized that something had changed in American anti-aircraft capability. The Americans had developed some new weapon or technique that dramatically improved their effectiveness. What that weapon was remained unknown. The fragments that Lieutenant Commander Sato recovered from Guadalcanal in August 1942 provided the first physical evidence. When the fragments reached Japan and were examined by ordnance specialists at the Yokosuka Naval Arsenal, the initial analysis revealed nothing unusual. The shell casing was standard American 5-inch .38 caliber. The explosive was conventional. The fragments showed no evidence of unusual propellants or exotic materials. But when technicians examined the fuse assembly more carefully, they found components that made no sense. Vacuum tubes, multiple vacuum tubes. In the nose of an artillery shell, the discovery was so unexpected that the initial analysis was rejected. Someone had made an error. The fragments had been mislabeled. These components could not be from an anti-aircraft shell. Vacuum tubes could not survive the shock of being fired from a gun. They would shatter instantly under the acceleration. The very presence of vacuum tubes in an artillery fuse was physically impossible. But as more fragments were recovered from subsequent engagements, as more shells were examined, the evidence became undeniable. American anti-aircraft shells contained vacuum tubes. The shells were using radio transmission to detect targets. The detonations were being triggered by proximity to aircraft rather than by preset timing. The Americans had solved a technical problem that Japanese scientists had considered theoretically insoluble. The implications were staggering. If the Americans could build vacuum tubes that survived artillery firing, if they could miniaturize radio equipment to fit inside a shell casing, if they could manufacture such devices in sufficient quantities for combat use, then American technological and industrial capability exceeded Japanese estimates by an enormous margin. The VT fuse represented not just a new weapon, but evidence of a technological gap that was wider than Japanese planners had imagined. Japanese scientists attempted to reverse engineer the captured fuse components. They examined the vacuum tubes under microscopes, measuring dimensions and analyzing construction techniques. They tested the tubes to understand their electrical characteristics. They attempted to fire similar tubes from guns to understand how they survived the shock. Every test failed. Japanese vacuum tube technology could not replicate what the Americans had achieved. The tubes they built could not survive firing. The few tubes that survived could not function under the centrifugal forces of shell rotation. Even when tubes were successfully fired and recovered intact, they could not reliably detect aircraft or trigger detonations with the precision the American fuses demonstrated. The technical gap was not in a single component or technique. It was comprehensive, spanning materials science, manufacturing processes, quality control, circuit design, and system integration. The Americans had not just solved one problem. They had solved dozens of interconnected problems, creating a complete system that functioned reliably in combat. Japanese industry in 1942 and 43 lacked the capacity to replicate this achievement. Factories were already strained, producing conventional weapons. Resources were limited. Skilled workers were scarce. The precision manufacturing and quality control required for VT fuse production exceeded Japanese industrial capabilities. More critically, the scientific knowledge base that had enabled American development did not exist in Japan to the same extent. American universities and research institutions had spent decades developing radio technology, vacuum tube theory, and electronic circuit design. American industry had commercialized these technologies through consumer products like radios and televisions, creating manufacturing expertise and supply chains that could be adapted to military production. Japan had some capability in these areas, but not at the scale or sophistication that American industry commanded. The recognition of this gap created profound unease among Japanese military leadership. The VT fuse was not Japan's only technological disadvantage. American radar was superior. American submarines used more sophisticated fire control. American aircraft featured better instruments and communications equipment. But the VT fuse was visible proof, physical evidence recovered from battlefields, that could not be dismissed or rationalized. The small fragment of sophisticated electronics in Sato's hand represented a manufacturing and scientific achievement that Japan could not match. By mid-1943, VT-fused shells were standard anti-aircraft ammunition throughout the American fleet. Every 5-inch gun carried a percentage of VT rounds in its ready magazine. Gunners loaded VT shells when engaging aircraft, conventional shells when engaging surface targets. The transformation in anti-aircraft effectiveness was dramatic and measurable. Before the VT fuse, American ships fired an average of 2,500 anti-aircraft rounds per aircraft destroyed. After the VT fuse became standard, the average dropped below 500 rounds per kill. The effectiveness increased by a factor of 5. This improvement translated directly into enhanced ship survivability. Japanese air attacks that would have previously succeeded in damaging or sinking American ships now failed with heavy aircraft losses. Kamikaze attacks in the war's final year, which relied on overwhelming anti-aircraft defenses through numbers, were devastated by VT fuses. Individual kamikaze aircraft were destroyed at ranges that gave them no chance of reaching their targets. Formations of kamikaze aircraft were shredded by VT-fused barrage fire that created zones of airspace lethal to any aircraft. The statistical impact is visible in loss rates. During the Okinawa campaign in 1945, American ships faced thousands of kamikaze attacks. Approximately 5,000 Japanese aircraft were committed to kamikaze missions against the invasion fleet. Of these, nearly 4,000 were shot down before reaching their targets. VT-fused anti-aircraft fire accounted for a substantial percentage of these kills. The shells that Japanese pilots could previously evade were now destroying aircraft with brutal efficiency. Japanese pilots flying in the war's final months understood they faced an unsolvable problem. American anti-aircraft fire had become so effective that survival was impossible. The shells exploded beside them regardless of evasive maneuvers. The fire was dense, accurate, and lethal at ranges that gave them no opportunity to escape. The VT fuse had transformed American anti-aircraft defense from a probabilistic system with low hit rates to a nearly deterministic system, where aircraft entering the defensive zone were likely to be destroyed. For Japanese scientists and military leaders analyzing the technological competition, the VT fuse represented confirmation of their worst assessments. The war was not just a struggle between military forces. It was a competition between industrial and scientific systems. The American system was producing weapons that Japan could not match. The gap was not closing. It was widening. Every month brought new evidence of American technological advantages that translated directly into military superiority. The fragments Lieutenant Commander Sato recovered in August 1942 told a story that extended far beyond a single new weapon. They told the story of why Japan was losing the war, the development of American industrial capacity that made the VT fuse possible, had roots that extended decades before the war. The story of how America built the capability to produce 22 million sophisticated electronic devices during wartime begins in the laboratories and factories of the 1920s and 30s, when radio technology transformed from experimental curiosity to mass consumer product. In 1920, perhaps 50,000 radio receivers existed in the United States, almost all of them built by hobbyists from individual components. By 1930, more than 10 million households owned factory-built radio receivers. This transformation from craft production to mass manufacturing created an entire industry with expertise in vacuum tube production, electronic assembly, quality control, and high-volume manufacturing. Companies like RCA, Westinghouse, and General Electric built factories capable of producing millions of vacuum tubes annually. They developed automated testing equipment. They established supply chains for raw materials. They trained thousands of workers in electronic assembly and inspection. When war came and the military needed similar capabilities for weapons production, the infrastructure already existed. The factories that had made radio tubes for consumer receivers could be retooled to make the specialized tubes for VT fuses. The workers who had assembled radios could assemble fuse components. The quality control systems that had ensured consumer products worked reliably could be adapted to military specifications. The supply chains that had delivered components to radio factories could deliver components to fuse production facilities. Japan had developed its own radio industry, but on a much smaller scale. Japanese households in the late 1930s numbered approximately 14 million. Radio ownership reached perhaps 2 million households, less than 15% penetration compared to over 70% in the United States. Japanese radio production was measured in hundreds of thousands of units annually, compared to American production measured in millions. The scale difference meant that Japanese industry had less experience with mass production, less automation, smaller supply chains, and fewer trained workers. This difference in scale translated directly into military production capacity. When the United States needed to produce millions of VT fuses, the industrial base existed to accomplish this task. Factories could be converted, workers could be trained, supply chains could be expanded. The fundamental knowledge and capability were already present, requiring adaptation rather than creation from nothing. When Japan attempted to replicate the VT fuse, the industrial base to support such production did not exist. Building it would require years and resources that Japan did not have. The technical sophistication of the VT fuse also reflected American investment in scientific research and development. The National Defense Research Committee, established in June 1940, coordinated research across universities, government laboratories, and private industry. The Office of Scientific Research and Development, created in June 1941, expanded this effort with funding that reached $450 million by war's end. This investment produced not just the VT fuse, but radar systems, sonar improvements, code-breaking computers, nuclear weapons research, and hundreds of other projects that enhanced American military capability. Japan had its own research programs, but with far less coordination and far smaller budgets. Japanese universities conducted weapons research. Military laboratories developed new technologies, but the integration between civilian scientific institutions and military needs was less developed than in the United States. The resources dedicated to research and development were a fraction of American spending, both in absolute terms and as a percentage of national budgets. The result was predictable. American weapons incorporated scientific advances that Japanese weapons lacked. American forces fought with equipment that reflected the latest technological developments. Japanese forces fought with equipment that was often a generation behind, designed with 1930s technology, and manufactured with industrial processes that had not significantly advanced since peacetime. The VT fuse exemplified this technological gap in a form that Japanese scientists could examine directly. The captured fragments provided concrete evidence of how far American capabilities exceeded Japanese estimates. By late 1943, Japanese naval intelligence had compiled detailed reports on the VT fuse based on captured fragments, pilot reports, and analysis of combat engagements. The reports acknowledged that Japan could not replicate the weapon with available resources and technology. They recommended tactical adaptations to reduce VT fuse effectiveness, changes to attack patterns, different approach altitudes, increased use of low-level attacks where VT fuses were less effective against sea surface clutter. But the reports also acknowledged that these adaptations could only marginally reduce losses. They could not eliminate the fundamental advantage that VT fuses provided to American anti-aircraft defense. The tactical recommendations were implemented throughout Japanese naval and air forces. Pilots were instructed to approach targets at very low altitude, skimming the wave tops where the VT fuse's radio signals might be confused by sea surface returns. Bombers were told to use terrain masking when possible, flying behind hills or through valleys where American ships could not engage them at long range. Kamikaze pilots in the war's final year were briefed to expect heavy losses from American anti-aircraft fire and to accept this as part of their mission. None of these adaptations significantly improved Japanese success rates. The VT fuse was only one component of American anti-aircraft capability, which also included radar fire control, superior gun mounts with faster traverse and elevation rates, better trained crews, and overwhelming numbers of weapons. A Japanese aircraft might evade VT-fused shells by flying at wave-top height, only to be engaged by 40mm Bofors guns or 20mm Oerlikon cannon at closer range. The layered defense meant that aircraft had to survive multiple engagement zones, each with weapons optimized for that range band. The Battle of the Philippine Sea in June 1944 demonstrated the combined effect of these American advantages. Japanese carrier aircraft launched massive strikes against the American fleet in what would become known as the Great Marianas Turkey Shoot. American combat air patrol fighters, directed by radar, intercepted Japanese formations before they reached the fleet. Those aircraft that penetrated the fighter screen encountered anti-aircraft fire of unprecedented density and accuracy. VT-fused 5-inch shells created a defensive barrier that destroyed aircraft at ranges exceeding 10,000 yards. 40mm guns engaged aircraft that penetrated the 5-inch barrier. 20mm cannon provided last-ditch defense at close range. Of approximately 375 Japanese aircraft launched in the strikes, approximately 300 were destroyed. American losses totaled 29 aircraft. The exchange rate was more than 10-1 in America's favor. Japanese naval aviation never recovered from these losses. The trained pilots who died could not be replaced. The aircraft lost represented a significant fraction of Japan's remaining carrier air power. The battle effectively ended Japan's ability to conduct offensive carrier operations for the remainder of the war. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Post-battle analysis by Japanese commanders identified VT fuses as a significant factor in the defensive effectiveness that produced such catastrophic losses. But the analysis also recognized that VT fuses alone did not explain the defeat. American radar allowed early interception. American fighter aircraft were superior in performance to Japanese types. American pilots were well-trained and adequately rested. Unlike Japanese pilots, who were increasingly rushed through abbreviated training programs, American ships mounted far more anti-aircraft guns than equivalent Japanese vessels. Every aspect of American capability exceeded Japanese capability by margins that were individually significant and cumulatively devastating. The VT fuse was not a war-winning weapon by itself. No single weapon could determine the outcome of a conflict as vast as World War II. But the VT fuse was symbolic of the broader pattern that defined the Pacific War. American industry could produce sophisticated weapons in overwhelming quantities. American science could solve technical problems that Japanese scientists found insoluble. American resources allowed the simultaneous development of multiple advanced weapons systems. American manufacturing could maintain quality control while producing millions of units. For Japanese scientists examining captured VT fuse fragments, the recognition of this disparity created a profound sense of futility. They were being asked to compete against a nation with 10 times their industrial capacity, superior scientific infrastructure, unlimited resources, and a technological lead that was widening rather than narrowing. The war was not just being lost on battlefields. It was being lost in factories, laboratories, and production facilities, where American advantages were insurmountable. Captain Aichi Iwaya, who served as an ordnance specialist at the Yokosuka Naval Arsenal throughout the war, later wrote about examining VT fuse fragments in 1943 and 44. His account, published in Japanese after the war, described the emotional impact of recognizing how far American technology exceeded Japanese capabilities. We knew we were behind in some areas. We knew American production exceeded ours, but seeing these fuse components, understanding what they represented, made the reality undeniable. This was not a gap we could close. This was a chasm that would only grow wider as the war continued. We were technicians and scientists. We understood the mathematics. We could calculate production rates and resource requirements. The conclusion was inescapable. We could not win. Iwaya's account describes how Japanese scientists continued their work despite this recognition. They analyzed every captured American weapon. They attempted to replicate advanced features. They developed incremental improvements to Japanese equipment, but they did so knowing that their efforts could not overcome the fundamental disparity in capabilities. The best Japanese science and industry could achieve was to slightly reduce the rate at which American advantages translated into military defeats. They could not reverse the tide. They could only delay the inevitable. The human cost of this technological gap was measured in the thousands of Japanese pilots and aircrew who died in the war's final 2 years. They flew missions against American ships, knowing that the anti-aircraft fire they faced was far more lethal than anything Japanese forces could deploy. They pressed attacks through defensive barriers that destroyed aircraft with ruthless efficiency. They died in enormous numbers, accomplishing missions that could not alter the war's outcome. The Kamikaze campaign in 1945 represented the ultimate expression of this futility. Japanese leadership, recognizing that conventional attacks could not penetrate American defenses, turned to suicide tactics, where success required only that the aircraft reach the target, not that the pilot survive. Kamikaze aircraft were loaded with explosives and fuel, making them even more vulnerable to VT-fused anti-aircraft fire. The pilots were often poorly trained, rushed through abbreviated programs that taught basic flying but not advanced combat maneuvers. They flew aircraft that were increasingly obsolete, older models pulled from training units because frontline aircraft were no praise, longer available in sufficient numbers. American ships engaged these kamikaze attacks with layered defenses that the Japanese could not overcome. Combat air patrol fighters, directed by radar-intercepted formations at distances exceeding 50 miles from the fleet, VT-fused 5-inch shells created barrier zones that destroyed aircraft at ranges between 10,000 and 15,000 yards. 40mm guns engaged at intermediate ranges between 2,000 and 5,000 yards. 20mm cannon provided last-ditch defense at ranges under 1,000 yards. Kamikaze aircraft had to survive all 4 engagement zones to reach their targets. Most did not. Of approximately 4,000 kamikaze aircraft committed during the Okinawa campaign, approximately 900 succeeded in hitting American ships. The success rate was below 25%. The aircraft that did succeed often hit smaller vessels like destroyers and destroyer escorts rather than high-value targets like carriers and battleships that were the primary objectives. The campaign sank approximately 30 American ships and damaged more than 300 others, inflicting significant losses. But it did not alter the strategic situation. American forces captured Okinawa. The fleet remained operational. The path to Japan lay open. Japanese pilots who flew kamikaze missions understood the odds. Many left letters describing their awareness that survival was impossible and success was unlikely. They flew anyway because military discipline and cultural values demanded that they accept the mission regardless of personal feelings. Some letters express belief in the righteousness of their cause. Others express resignation to fate. Few express any expectation of meaningful military impact. They were young men, often barely 20 years old, sent to die in aircraft that could not protect them against defenses they could not overcome. The VT fuse contributed to this toll. Every kamikaze aircraft destroyed by VT-fused anti-aircraft fire represented a death that might have been survivable had the shell exploded in empty air rather than beside the aircraft. The statistics suggest that VT fuses increased American anti-aircraft effectiveness by approximately 5 times compared to mechanical time fuses. If this factor is applied to kamikaze losses, potentially several hundred additional aircraft might have survived to reach their targets had VT fuses not existed. Whether this would have changed strategic outcomes is doubtful. American numerical advantages were so overwhelming that even significantly higher kamikaze success rates would not have prevented American victory. But for the individual pilots who died when VT-fused shells exploded beside their aircraft, the distinction was meaningless. They were dead either way. The end of the war in August 1945 left Japan with captured stockpiles of American equipment, including thousands of VT-fused shells. Post-war analysis by Japanese scientists provided the complete picture of what the VT fuse represented technically and industrially. The reports acknowledged that Japanese technology in 1945 still could not replicate the VT fuse's performance. The vacuum tubes remained beyond Japanese manufacturing capability. The miniaturization exceeded Japanese electronics industry standards. The quality control necessary for reliable performance in combat was beyond what Japanese factories could achieve. These reports concluded that the VT fuse exemplified the comprehensive nature of American technological and industrial superiority. It was not one breakthrough that had won the war. It was hundreds of incremental advances across multiple fields, cumulative advantages in manufacturing, science, resource access, and skilled labor. The VT fuse could not have been developed without decades of investment in radio technology, electronics manufacturing, vacuum tube production, and scientific research. It could not have been produced without factories capable of high-volume precision manufacturing, supply chains delivering components reliably, and quality control systems ensuring consistent performance. Japan in the 1930s and 40s lacked these prerequisites. Building them would have required decades of peacetime development, resources Japan did not have, and strategic choices Japan did not make. The decision to go to war with the United States in December 1941 was a decision to fight an opponent whose industrial and technological capabilities exceeded Japan's by margins that made defeat inevitable. The VT fuse was simply one of many visible proofs of this disparity. American forces ended the war with approximately 22 million VT fuses produced and approximately 10 million expended in combat. The remaining 12 million fuses represented stockpiles that would have been used in the planned invasion of Japan, scheduled for November 1945. Those fuses were never fired. The war ended in August after the atomic bombings of Hiroshima and Nagasaki and the Soviet invasion of Manchuria convinced Japanese leadership that further resistance was futile. The VT fuse continued in American service long after World War II ended. During the Korean War, VT-fused anti-aircraft shells protected American forces from Chinese and North Korean air attacks. During the Vietnam War, VT fuses were used against North Vietnamese aircraft. The basic design remained effective for decades, testament to how far ahead of its time the weapon had been when first deployed in 1943. Modern proximity fuses use solid-state electronics and more sophisticated detection methods, but the fundamental principle remains unchanged. Detect the target using radio signals, calculate when the shell is at optimal range, detonate for maximum lethality. The legacy of the VT fuse extends beyond its direct military impact. It demonstrated that scientific research and development could produce weapons that fundamentally altered combat effectiveness. It showed that investment in civilian technology like radio could have direct military applications when war came. It proved that mass production of sophisticated electronics was possible with proper manufacturing techniques and quality control. These lessons influenced American military policy for the remainder of the 20th century and continue to shape defense planning today. For Japan, the VT fuse's legacy was the recognition that technological competition between nations could determine military outcomes as surely as battles between armies. The nation that had entered World War II believing that fighting spirit and tactical skill could overcome material disadvantages learned through bitter experience that modern industrial war rewarded the nation with superior technology and production capacity. No amount of courage, training, or devotion could compensate for being equipped with weapons that were a generation behind the enemy's capabilities. Lieutenant Commander Sato, who had picked up those shell fragments on Guadalcanal in August 1942, survived the war. He returned to Japan in late 1945 and eventually joined the Maritime Self-Defense Force when it was established in the 1950s. In interviews conducted decades later, he described the moment of examining those fragments as the instant when he first understood that Japan would lose the war. The fragments contained vacuum tubes. This should have been impossible. That it was not impossible meant the Americans could do things we could not do. Everything that followed, all the battles, all the losses, all the defeats, was simply the working out of that reality. We were fighting an enemy who could make shells that hunted aircraft. We could not make such shells. The conclusion was obvious to anyone who understood the implications. Sato's assessment, shared by many Japanese scientists and military officers who examined American equipment during and after the war, highlights the psychological impact of confronting technological inferiority. It was not just that American weapons were better. It was that American weapons demonstrated capabilities that Japanese experts had considered impossible or impractical. The VT fuse fell into this category. Japanese scientists in the late 1930s had discussed proximity fuse concepts. They had concluded that the technical challenges were insurmountable with available technology. The Americans had solved problems that Japanese scientists had dismissed as unsolvable. This pattern repeated across multiple technologies. Japanese radar was inferior to American radar. Japanese scientists had believed their designs were adequate. American submarines used superior fire control systems. Japanese submarine commanders had believed their equipment was sufficient. American bombers featured better instrumentation and navigation aids. Japanese bomber crews had believed their aircraft were comparable. In every case, combat experience revealed that Japanese assessments had been optimistic, underestimating both American capabilities and the importance of technological advantages in determining combat outcomes. The VT fuse represented this pattern in miniature, a single weapon system that encapsulated the broader technological competition. When Japanese scientists examined the fuse fragments, they were not just analyzing one weapon. They were confronting evidence that the entire Japanese assessment of relative technological capabilities had been fundamentally wrong. The Americans were not slightly ahead in a few areas. They were significantly ahead across multiple domains. The gap was not static. It was widening as American industrial and scientific capacity outproduced and out-innovated Japanese efforts. For the thousands of Japanese pilots who died in the war's final years, the VT fuse was simply one more hazard among many that made survival impossible. They flew inferior aircraft with inadequate training against opponents who had every advantage in numbers, technology, and tactics. The VT-fused shells that exploded beside them were no more or less deadly than the fighter aircraft that shot them down or the mechanical failures that came from overworked engines and poor maintenance. They died because they were fighting a war that Japan could not win, equipped with weapons that could not match American capabilities, supported by an industrial base that could not sustain the necessary production. The story of the VT fuse is ultimately about more than a single weapon. It is about the industrial and scientific competition that underlay the military conflict. It is about how decisions made in peacetime about resource allocation, industrial development, scientific research, and technological investment determined wartime outcomes. It is about the consequences of fighting an opponent whose advantages were so comprehensive that no tactical innovation or strategic brilliance could overcome them. The fragments that Lieutenant Commander Sato recovered on Guadalcanal told this story in physical form. The vacuum tubes that should not have existed inside an artillery shell existed because American industry had spent decades developing the capabilities to make them exist. The radio circuits that should not have functioned after being fired from a gun functioned because American scientists had solved problems that Japanese scientists considered unsolvable. The fuse that should not have been producible in military quantities was being produced by the millions because American factories had the scale, automation, and quality control to accomplish what Japanese factories could not. When Japanese scientists examined these fragments and understood what they represented, they understood that the war was lost, not because of any single battle or campaign, not because of any tactical or strategic error, but because Japan was fighting an opponent whose industrial and technological capabilities exceeded Japan's by margins that could not be overcome. The VT fuse was proof, tangible physical evidence that could not be dismissed or rationalized, that American capabilities were fundamentally superior to Japanese capabilities in ways that would determine the war's outcome. The recognition came too late to matter. By the time Japanese scientists fully understood what the VT fuse represented, the strategic situation had already deteriorated beyond recovery. American forces controlled the Pacific approaches to Japan, The home islands were under blockade. Strategic bombing was destroying Japanese cities. The atomic bomb was months away from deployment. Whether Japanese scientists understood American technological superiority or not made no difference to the war's outcome. But for the individuals involved, for Lieutenant Commander Sato, holding shell fragments on a beach in Guadalcanal, for Captain Iwaya examining vacuum tubes in a laboratory at Yokosuka, for the thousands of scientists and engineers who tried to reverse engineer American weapons, the recognition was profound and personal. They had dedicated their lives to serving their country. They had believed their efforts mattered. They had trusted that Japanese science and industry could compete with any nation. The VT fuse and dozens of similar American weapons proved these beliefs wrong. The war had been decided not by courage or determination or fighting spirit, but by production capacity and technological capability. The nation with superior factories, better scientists, more resources, and advanced technology would win. The nation with inferior capabilities in these areas would lose. No amount of sacrifice by soldiers, sailors, or airmen could change this fundamental reality. They could die with honor, they could fight with skill and courage, but they could not overcome the gap between what Japan could produce and what America could produce. The VT fuse remains in museums and collections, a testament to American scientific and industrial achievement during World War II. The shells themselves are inert, the electronics long since dead, the batteries exhausted, but they represent something more significant than their physical components. They represent the moment when warfare became fully dependent on industrial and technological capability, when victory required not just military skill, but manufacturing capacity and scientific knowledge. For Japan, the VT fuse represents the evidence that could not be denied, the proof that the war was unwinnable from the moment it began. The shells that exploded in mid-air without hitting anything were not magic or luck. They were the product of decades of American investment in science, technology, education, and industry. They were the inevitable result of a competition between nations, with vastly different capabilities. They were the physical embodiment of why Japan lost the Pacific War. The fragments Lieutenant Commander Sato recovered in August 1942 sit in archives now, labelled and catalogued, their significance understood by historians and researchers. They are not dramatic or impressive to look at. They are small pieces of metal and glass, corroded by salt water, damaged by impact and explosion. But they told the story of the war as clearly as any battle report or strategic analysis. They told the story of how America's scientific and industrial strength created weapons that Japan could not match, could not counter, and ultimately could not survive against. In the end, the VT fuse was just one weapon among thousands. It did not win the war by itself, but it was symbolic of everything that did win the war: the comprehensive American superiority in technology, production, resources, and scientific capability that made Japanese defeat inevitable. The pilots who died when VT-fused shells exploded beside them were casualties not just of that specific weapon, but of the entire industrial and technological competition that determined the Pacific War's outcome. They were sent to fight with equipment that could not protect them against weapons they could not overcome, launched from ships they could not sink, by an enemy they could not defeat. The VT fuse simply made this reality more efficient, killing them at longer ranges with greater certainty than mechanical time fuses had done. The result was the same. The war was lost. The industrial and technological gap was too wide. The competition was over before it truly began. The shells that Japanese gunners examined, trying to understand how they exploded in mid-air, represented the answer to why Japan lost. Not because Japanese soldiers lacked courage or skill, not because Japanese commanders made fatal errors, but because Japan had chosen to fight an opponent whose scientific and crises aplomb industrial capabilities were so superior that defeat was inevitable. The VT fuse was simply the proof, the physical evidence that made this reality undeniable. For historians examining this period, the VT fuse serves as a case study in how technological advantage translates into military superiority. For military planners today, It demonstrates the importance of investing in research, development, and manufacturing capability during peacetime. For those interested in World War II history, it provides insight into why the Pacific War ended as it did, with total American victory and complete Japanese defeat. The outcome was determined not primarily by battles, but by the factories and laboratories that produced the weapons those battles were fought with. The VT fuse was one of those weapons, not the most dramatic, not the most famous, but representative of the pattern that defined the war. American science solved problems Japanese science could not solve. American industry produced weapons Japanese industry could not produce. American forces fought with equipment that Japanese forces could not match. The result was inevitable. The recognition came slowly for Japanese forces, engagement by engagement, weapon by weapon, defeat by defeat. But once recognized, the conclusion was inescapable. They could not win. They never could have won. The competition was decided by capabilities developed years before the first shot was fired. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.